Hi everyone, myself and Arun Kumar from SNS College of Technology in the Department of ECE. In this video, we are going to discuss about root locus technique and constructions. Generally, the root locus are framed based on the number of poles which is located in the S-plane. Let me discuss what are the things we are going to analyze in this PPT. First one is introduction and the root locus techniques. Explain for a root locus, rules for root locus, construction of root locus, and application and assessment. So these things we are going to discuss about this PPT. So introduction. The main purpose of this root locus is a graphical method used in a control system engineering to study how the roots of a system has been analyzed based on the characteristic equation, because the poles are the one which is used to identify the concern poles in the region based on the margin of a system, so that we can able to catch the frequency response of the system. And moreover, it helps the visualize stability and transient response of a system. The root locus method shows how the pole location changes based on the gain process. And moreover, it is very useful to find the number of input frequency based on the time invariant systems. And root locus starts at the open loop poles and ends at the open loop zeros. So based on the poles and zeros, we can able to identify the concern frequency response of the system. So we need to design a root locus based on the number of rules. The following rules we need to consider while designing a root locus technique. First one is locate the open poles and zeros in the S-plane, and second, find the number of root locus branches, and third one, identify and draw the real axis root locus branches, and fourth one, from the centroid point, find and the angle of asymptotus technique. And next one is find the breakaway and breakpoints. And next one is find the angle of departure and angle of arrival. And last one is intersection point on imaginary axis. First one is explain. While designing poles at the location, we need to know about S-plane, because based on the number of poles only we have to mark it the concerned frequency based on imaginary and real axis method. So in real axis we need to mark the number of poles which is present from the characteristic equation based on the positive and negative values. And second diagram shows that if it is plot the pole as -2 means, then the corresponding real and imaginary axis has to be mapped by using this asymptotus technique. The asymptotus is the one which is identified to locate the number of poles based on the angles. If the angle is 60-degree means, then the corresponding poles has to be mapped based on the 60-degree towards the imaginary axis. So let me see how this S-plane has been mapped by using a characteristic equation. So now we are having some characteristic equation as g of s and h of s equal to k by s into s plus 1 and s plus y. The first step is we need to map the number of poles. The number of poles are mapped based on the number of equating zeros. First one is s equal to 0, and then next one is s equal to -1 and s equal to -5. Suppose in your problem they are given about the equation as s square into like that they are given. We need to use some formula like a minus b plus or minus root of b square minus 4ac divided by 2a. This is the characteristic equation for a system. We need to use that equation so that we can make it as the equation become a s value. So after getting the s value, we need to map the concerned value in s map. So the value has been mapped in S map like 0, -1 and -1. All three values as mapped in this S plane. It is a P1 and it is a P2 and it is a P3. So all those three values are considered as a poles. It is mapped in the S plane. Our next step is we need to calculate the centroid because each value of the poles must be mapped in the centroid point. Based on the centroid point, we need to map the corresponding value in a imaginary axis. It is calculated by sum of poles minus sum of zeros divided by n minus m. So in this problem, we are having sum of poles is 3 and minus zeros is sum of 0 is 1. So 3 minus 1, 2. So like that 3 minus 2, value has been calculated as a centroid point. And next one is asymptotus. This asymptotus is the value of angle. It is calculated by 180 2q plus or minus 1 into divided by n minus 1. So like this formula, we can able to substitute the quadrature value as 0, 1, 2, 3, 4. So we need to check which kind of quadrature has been mapped for this particular poles value. So it is mapped based on 60, 180, 300 degrees. So we can consider 60 as our primary value for making all those poles into the region. So finally, they are making this equation based on the centroid point. Already we are getting the centroid point as minus 2. So minus 2 is to be marked in this region. So after marked the minus 2 centroid point value, we need to plot the angle. So while considering this as a 60-degree angle, it is placed to the real and imaginary axis, because it is from a real axis, then it is passed to the imaginary axis. Like this, the both the poles plus and minus has to be mapped by using this centroid point value. And next one is breakaway point. So this break point can be calculated by the equation, characteristic equation. This equation as formed based on 1 plus g of s into h of s. So g of s equal to g of s divided by 1 plus g of s into h of s. So after cancelling all those value, we have a break point as minus 0.473. So this is the break point of the concerned characteristic equation into the poles of the concerned region. So based on this equation, we need to map this equation into the imaginary axis. The imaginary axis of this concern method is calculated based on the Routh-Horvitz method. Finally, we get the answer as j5 minus root 5. So this value has been mapped along with this breakaway point in the next step. So the plus or minus j root 5 plus minus j root 5 as mapped based on this breakaway point as a minus 0.473. So this is the breakaway point in between the imaginary and real axis. Already we have calculated the centroid point along the angle 60 degree. Now we are going to map the concerned poles as centroid point, and based on the centroid points, we need to locate the breakaway points in between the imaginary axis and real axis. The breakaway point between the imaginary and real axis is 0.473. So this is the point which is to be mapped between the real and imaginary axis. So like this, it can be mapped up to j root 5 minus j root 5. So this is the root locus technique which is to be placed based on the breakaway point and centroid point. So sufficient condition for the Routh Horvitz stability. All the elements of the first column of the Routh array are positive. Then there is no sign changes in the first column of the Routh array. So the control system is a stable system because we are having the value as the same one. Applications. The root locus plot technique can be applied to determine the dynamic response of the system. This method associates itself with the transient of the system and is particularly useful in the investigation of stability characteristic of a system. And the root plot technique is essential for a time domain application technique, and most probably it is used to determine the stability boundaries of a system. Assessment. Let us take an example of a drone control system as an open loop transfer function g of s k s into s plus 3. Determine the range of k for stability and analyze the root locus. So initially we are going to calculate the pole value here, s equal to 0 and s equal to minus 3. Then the root locus is lie between the axis poles and extend left from s equal to 0. Then the system is said to be stable as long as both poles remain in the left half of the S plane, because 0 less than k less than 9. So we are having only the values become 0 to 9. So beyond the k equal to 9, only one pole enters the right half of the plane, so it causing a instability because it is extend the level of 0 and above the level of poles value. So it makes a instability effect which causes in the loop transferring system. Thank you.